Section 5.4, page 2. So we had ended the previous video finding the derivative of the function that is equal to the integral of another function from some constant to an x value. And the derivative we saw was essentially equal to what looked like the function we were integrating. So let's elaborate on that. The fundamental theorem of calculus has two parts. We need to have a constant or continuous, function, not constant, a continuous function from A to B. And we've already discussed the fundamental theorem of calculus part 2 in section 5.3, but now we're going to use what we just discussed above for part 1. If there is a function g of x that is equal to another function f of t that's being integrated over the variable t from a being a constant to some point along the ab interval but not all the way across, then the derivative of that equivalent function is essentially equal to the function being integrated over the x value. So very simplistic way of thinking about it is you're plugging x into the integral function, although we'll see it's a lot more advanced than that. But starting off with that simple example, I'm asked to find the derivative of the functions. So essentially the derivative of the g of x function, which I've got here. But how did I get that? Well, according to the fundamental theorem of calculus part 1, I can take that function being integrated, the t to the 8th, and I can essentially just plug x in where t was. So where t was, I'm going to plug in x. Of course, we saw all of the steps up above, how to mathematically get there using the fundamental theorem of calculus part 2, where we're evaluating at our constant, whose derivative will always be 0, and the x value, which is somewhere in our continuous range. Now here's where it gets a little more complex. I've got my g of x function for this second example. Same looking problem, but instead of integrating from my constant 0 to just x, I'm integrating to x value that is 3x. It's not quite just x alone. So what's going to happen is I need to use the chain rule, and let's explain why in a second. But we are going to essentially evaluate this function where we're going to have to take the antiderivative, and we're then going to plug this value in. So we'll have some other g of x function with some information off to the side. When we evaluate it at 3 of x, that gets us our new function. But when I take a derivative, I'm going to have that 3x to the 8th power, and in a derivative, I would then need to take a chain rule. I can't ignore the fact that I didn't have x alone. So the derivative of 3x is 3, right? You could argue I took the derivative of x here. It was just 1. So the derivative of 3x, not 3x to the 8th. Remember, just the interior function is 3. And we'll go ahead and leave our answer this way. You could write this as 3 to the 9th, x to the 8th. You could even calculate 3 to the 8th, but we won't get that elaborate. Two twists on this kind of problem. Over here, I've got another g of x problem. I still have that t to the 8th. But remember, I'm supposed to have a constant, but I don't have that down below. I'm supposed to have a variable x. I mean, it could be v or q, so long as it's the same variable that's the input for my g function. But I don't have that. But wait a minute, they're just flip-flop from where I would like them to be. So what we can do is use our integral property that instead of integrating from x to 3, I can integrate from 3 to x, but I need the opposite or inverse of the function I had. So inverse maybe sounding correct for this, but essentially it's like, think of it as multiplying by -1. So the only difference between these top two examples is going from a constant to a point in the variable. So we're just going to have the negative sign out front. And the last twist is requiring another property of integrals, Again, I don't have a constant that I'm beginning my integration from, but I do have a variable that I'm stopping at. So I've got my t to the 8th, just like before. Well, here's the thing. What I really wished is I was integrating, ignore this for a second, and I was integrating from 0 to, well, actually, let me rephrase that. It's already starting here. I'm integrating from some constant to 2x, but remember, to integrate, I need these two values to match. So if I had my 0 and my 2x, then these would have added back up to integrate from 3x and 2x. So what I'll do is, instead of putting the 0 up top and the 2x on the bottom, I'm going to use the integration property where I can flip it, and then I can add it to another integral that does start from a constant. Hopefully I explained that well without seeing all these steps. So this individual problem we've already solved. Oh, but wait a minute. I'm not just plugging in x, I'm plugging in 2x. So I needed to do a chain rule, take the derivative of 2x. And same thing, I needed to take the derivative of 3x. And I'm fine if we just go ahead and leave the answer this way, unless you're told to evaluate further. The very last concept we're going to study in this section is the average value of a function. Let's begin by just thinking about the average of a set of numbers. To find the average of a set of numbers, for example, 2, 2, and 8, we add up those numbers, we divide by the fact that we had 3, and we found an average of 4. Remembering that the point of an average is these values don't all have to be the same, but what is the number that would result as if they were the same? Well, if these had been, instead of a 2, it was a 4. Instead of another 2, it was a 4. Instead of an 8, it was a 4. If we took the average of these numbers, we still get 4 out. So you can almost think of it as standardizing all of the values. So formally, to write this out, we have some y function that can be an average where we're going to add up all of the outputs and divide by how many outputs there were. That's why we have y to the n summed up through n. So here's the thing though. We are doing rectangles. You could think about it as area under curves, right? But we said we're going to be far more accurate if we have an infinitely many of rectangles. So normally we take the limit as this n goes to infinity, infinite number of rectangles. So I'm taking this line again, saying the average is approximately this, but let's go ahead and talk about as if that function were equal. I just stated this function, but have seen n in other places, and we don't really want to have to know what n is necessarily. So remembering that the number of rectangles n that we use determines the width of each rectangle, then let's take this equation and solve for n. So I'm going to multiply both sides by n. I'm going to divide both sides by delta x, and I'm going to end up with n was essentially b minus a over delta x. But when you have a fraction divided by a fraction, although I guess the top doesn't look like a fraction, but it's part of one, we can instead multiply by the reciprocal, which is all we did. And if you notice here, this should look really familiar. We're adding up a bunch of heights of rectangles or outputs of a function where each one is multiplied with the width. Well, if we're taking the limit as n goes to infinity of these, this is our formula for the integral from a to b of f of x. So the only piece that's new is we're multiplying that integral by 1 over b minus a, so the reciprocal of the width of the area we're integrating.